Buenos dias. I want to show you guys a kind of a sketch of why this nine-summand summation. There's 9 summands. 173 minus 65 plus 1. You have to add 1. It's sort of counterintuitive. But there are 9 summands here. And let's draw a picture. It's summing up the square roots of 165, 166, all the way to 173. So let's get a little pick on why this is believable. Okay, we'll draw the square root function here. Of course, it goes through the origin. Increases fairly slowly. It's a concave down in calculus vernacular. That means it increases at a decreasing rate. But notice that 169 is over here somewhere, right? And the square root of 169 is 13. So let me locate this point up here. Okay, so you have the point 169, comma 13. And of course, this is the graph of y is equal to the square root of x. Okay, so you see there it is almost, folks. You see 13, right? There's 9 summands. The square root of 169 is in the middle of this, right? It's in the middle of this. And notice that 9 times 13 is 117. So that's not a proof, but it's very believable if you remember that the graph of the square root function is concave down, which means it's increasing at a slower rate as you move along. Okay, so it's very believable that this would be strictly less than 117. Now let's go through the formality of it. This is the Cauchy Schwarz inequality. It has its roots sort of in linear algebra, where you can think of this as an inner product in linear algebra. Now, notice that the equality condition occurs if you have the ratios equal to each other, and that's not going to happen in this case. You'll see why in just a minute. Now, y'all, I rewrote this in a way that's a little more palatable. You see, you had greater than or equal to. I just wrote it less than or equal to. Because you see, we can write our left-hand side as 1 times the square root of 165 plus 1 times the square root of 166 plus 1 times the square root of 173. That is our inequality squared, right? Now, that's our statement squared. Now, we put the 1 there for a very convenient reason, because they become our a sub i's, you see. So in other words, what you would really have right here, so you'll know you don't have equalities, you would have 1 over the square root of 165. It doesn't matter what order you do it to. You can reverse you can reciprocate. Okay, that's not equal to. So it has to be equal if you want equality to occur in the inequality, and so you have 1 over the square root of 166 right here, and so on. Right? So you see this is the equality condition. It's essentially if all the coordinates are points on the same line. Okay, and if you look at the proof of the Cauchy Schwarz, you can see why all that's true. But in any event, I've gone through all the arithmetic here for you. Notice that I squared the square roots. I tried to line all this up perfectly for you so you can see where all this comes from. Okay, so the arithmetic turns out to be fairly straightforward. We get that our inequality of interest, after we take the square roots, see, we took the square roots going from here to here. Okay, so this is our original inequality. And then this right-hand side becomes this, square root. You can put 2 square roots together. And so now the hardest computation is adding up 165 all the way up to 173. You can do that, folks. That computation, adding up this piece right here, is the same. We have 9 terms, right? So you can think of 9 over 2 times the sum of the first and last terms. It's an arithmetic sequence, actually, okay? And this is a little bit easier, the computation-wise, to do, right? You have to do to it add up the first and last term, and then multiply by 9/2. So 9 is the number of terms it's just the number of terms. Okay, so 173. Okay, and that ends up being this 1521 that you see right here. And so what do we get right here? This is equal to 3 times 37. Right, and isn't that 3 times 37, 3 times 40 is 120, subtract 3, you get 1. Oh no, sorry y'all, this is 39, I believe. Yeah, 3 times 39, because 39 squared, let me write this up here just to avoid the confusion. 39 squared is equal to 1521. Okay, so 3 times 39, 3 times 40 is 120, so this would be the 117 we're looking for, folks. So there's your Cauchy Schwarz proof, folks. Hopefully it was clear enough. Just the proof of Cauchy Schwarz, I did a video on that. It's pretty neat. It's based on looking at this expression, a sub I times x plus b. And then you actually do a quadratic equation, look at the discriminant, you can actually prove the Cauchy Schwarz inequality, thinking of it from this perspective. In our case, I would be, our n is equal to 9 here. Okay. But in general, it's fun to go through it's actually pretty easy, really. You look at the discriminant being negative, I believe, and you can actually prove the Cauchy Schwarz pretty quickly. But anyway, y'all, we've proved it. I like this intuitive look right up here. You know, because the square root of 169 is in the middle, but this isn't linear. So the concavity of the square root function, concave down nature of it, makes it very easy to believe that this would be less than without going through this relatively tedious computation. And y'all, by the way, this is called the one trick. It's popularized in a book, by a famous guy up north who did the Cauchy masterclass, and I'll put a comment about that in the description. Okay, so this is QED time. We got 117 right here, and that's what we were trying to show, so we're done. Okay, thanks for viewing.